Hi everyone, just going to be running through some examples again through the new book for Black Belts, Six Sigma Statistics using Minitab 18 Black Belt Edition. If you want to work along with us, you can download the data sets from my website rmk6sigma.com. Hi everyone, it's 21st of June 2020. I hope you're all well. I'm just going to be doing a tutorial video based around my book Six Sigma Statistics using Minitab 18 and the Black Belt Edition. If you want to work along with the tutorial, you can download the data sets from my website rmk6sigma.com. The intention is that it's going to be a series of 3 videos on logistic regression. Now, you've probably done regular regression before, so in regular regression you have a continuous response, but in logistic regression we have a categorical response, and we can either have logistic regression being binary, ordinal or nominal. So with binary, bi indicating 2, so we only have 2 states to the response, for example on and off on a light bulb, head and tails, or yes and no. With ordinal logistic regression we have more than 2 responses, but they have an order. You can give them a value system, for example gold, silver, bronze in the medals table at the Olympics. Let's say for your degree level, you can either get a first, a 2-1 or a 2-2 or a 3rd degree. In an exam you get grades like A, B, C and D, and we perceive value to those grades. So with nominal logistic regression you have more than 2 categorical type levels of the response, but you don't necessarily give them an order value. So let's say people's TV's watching habit. You can either be watching sports, documentaries or fiction, so we can't particularly order those unless we really want to be argumentative, I suppose. Even when you're rolling a die, if we don't assign an order to the values 1, 2, 3, 4, 5, 6, you can have those as a nominal response. So this video is going to focus on when we have a binary response, and the tools that we're going to be looking at in Minitab are the binary fitted plot and binary logistic regression. So the binary fitted plot is a lot like the fitted line plot that you've used in regression before, where you have one numerical predictor against the response. And then binary logistic regression is where you can have from 1 to many predictors, and they can be continuous or categorical predictors against the binary response. So we just need to go through some terminology as well, and this terminology applies to ordinal and nominal regression as well. So the first thing is that trials need to be independent. So if you were tossing a coin and you threw 10 heads in a row, what's the chance that that would affect your 11th row? Well, if the trials were independent, it wouldn't affect your 11th row, and the probability for throwing a head or tail would still be 50%. So trials are independent. And also the responses need to be exhaustive. So if we go back to our coin toss example, the responses are exhaustive because you can only throw a head or a tail. Yeah, you could argue that it's going to land on its head, and there is a small chance of that, but I've never ever seen that happen in my 50 years, so that's never going to happen, and we've captured the 2 outcomes that you can possibly have. And the final thing I need to go through is link functions, which I'm going to be doing in the next 2 slides. Okay, let's pretend we've got a continuous predictor against a binary response. We can code our response values as 0 and 1, and whichever response value we like more, we can call that the reference event. So in that case we give it a value of 1, and that's what's drawn out on a scatter plot on the top left. As you can see, as the value of our predictor increases, we've got more of a chance of going to our reference event of 1. So in the bottom plot we can use our normal regression routines to give us the line of best fit for this system. But like a clock that's stopped, it's only right on 2 occasions. So a better option for us is not to use standard regression, but to use logistic regression. So what that does is it maps the area between 0 and 1 into a probability of the reference event occurring. So then by default Minitab uses the logic function as the link function, and that's a lot better than the other 2 link functions that are available. However, Sometimes it doesn't work out so well, and you do need to then change the link function that you're using and try one of the other functions to see which one gives you the best regression model. So the link function is a log transformation, hence the name logistic regression. So logistic regression is used to understand if the slope of the untransformed link function is statistically significant for any of the predictors, i.e., or is it any different to a horizontal line. So now we understand a bit more about the link function, we're going to look at the binary fitted plot and then work towards binary logistic regression. The example that we're going to be looking at from the Black Belt edition is example 7.2.3, and it's based around the monarch butterfly. So if you want to get the data sets and work along with us, you can download those from RMK Six Sigma. So I'm just going to read out what's required in this example. So lepidopterists classify the monarch butterfly depending upon its weight. Ikra, my daughter, wants to know if they can also be classified according to their wingspan. She collects data on 40 butterflies and measures the wingspan and then classifies them as either large or medium sized depending on the weight. For this study, assume that all the small ones were not included in the study. What we are required to do is to evaluate, number one, if there is a statistically significant link between wingspan and the binary response size. Number two, if a butterfly with a wingspan of 22.5 is likely to be classified as large or medium. And number three, evaluate what is the change in probability of classifying a monarch as large with a 3 mil increase in wingspan. Okay, I've got Minitab open, and here's my two columns of data. The first one is size, which is my response data telling me the size of the butterfly, and the second one is the continuous data for the predictor, which is telling me the wingspan. So what I know is, can I use wingspan to predict the response, i.e. will it be classified as a large butterfly or a medium butterfly? So I can do that using the binary fitted plot. So I need to go to Stat, Regression, Binary Fitted Plot, and it opens up there, and the first drop down I get is asking me how my data is recorded in the spreadsheet. I need to select my response column is size, and I want to call my reference event, I want to call that large, and my predictor is wingspan. Click OK to execute the procedure. Now let's just go to the session window and have a look down the results. Okay, under method we can see that the logit link function was used. We had 40 rows of data. For response information, you can see that I set large as the reference event, and for the response data we had 20 data points as large and 20 as medium, so a good spread. Then the deviance table tells us that our predictor wingspan had a p-value of 0. Therefore it is significant, and we can use it to predict the size of the butterfly. Model summary gives us an R squared of 60.3%, but we can use these three metrics and try different link functions and see if any of them gives a better result. Usually we stick with logit because that gives us our odds ratio. So here we have odds ratio down here. Now that's telling us for a change in wingspan of 1 unit, the probability of getting the reference event occurring will increase by a factor of times 2.5. Okay, and what I missed out was coefficient. So wingspan has a positive coefficient of 0.931. So this is telling me as wingspan is increasing, the probability of my reference event is also increasing. We then have the regression equation, and it seems quite a complicated equation for the probability of getting the reference event. Now you need a complicated equation like that to get a nice curve as we did. So let's have a look at the curve then. So we've already answered the first question. We can use wingspan to predict the size of the butterfly. The second part of the question says, okay, if you have a wingspan of 22.5, will the butterfly be classified as large or medium? So what I can do is I can add reference lines onto this plot to help me. Add. Right click, then go on to add, then reference lines. I want to put a reference line at a probability of 50%, so 0.5, and the wingspan I'm interested in is 22.5. Okay. So the wingspan of 22.5, if I draw that line up, intersects with our regression line below 50%. So more than likely that butterfly will be classified as medium. But we are now black belts, we know about confidence intervals. So let's redraw this plot with confidence intervals. So click on the icon for edit last, go on to graphs, select it for display confidence interval, click OK and OK again. So we now have that plot with confidence intervals. Let's add the same reference lines again, 0.5 and 22.5. Okay, so although we'll probably be classifying the butterfly as medium, the probabilities from the confidence intervals tells us that the probability of classifying the butterfly as large is somewhere between around 15% and about 65%. So there's quite a range, as you can see, of probabilities, but more than likely it still will be classified as medium. So that answers the second part of the question. In the final part of the question, we're being asked what would be the change in probability of getting a large classification if the wingspan were to increase by 3. So essentially it's saying what would be your odds ratio if your wingspan increased by 3. So we can change that by again clicking onto the edit last icon, clicking on options, and there you can see the increment for odds ratio is set to 1 as default, and we can change that to 3 and execute the procedure again and go to the session window and have a look at the odds ratio. So there's the odds ratio there. So if the wingspan were to increase by 3, the probability of classifying our butterfly as large would increase by a factor of 16.3. That answers the third part of the question, and because we're black belts, we know we should have a look at the residuals. So again, we need to execute the procedure again. So I'm going to go to edit last, graphs, and click on the residual plot to produce the 3-in-1 plot. Click OK again. OK. Let's have a look at the residual plot. So the normal probability plot looks quite good. You could put a fat pencil across there, barring one point. Let's have a look at which point that is. So row 9 has a high residual, and on the versus order, I bet that's row 9 as well. Yeah, that's row 9. And again, I bet that's row 9 as well. So there's only one point that's giving an issue, so row 9. Apart from that, the study looks okay and is validated. So that concludes the binary fitted plot example. For binary logistic regression, we've got example 7.2.6 called Sci-Fi. Again, you can download the Excel sheet and work along with us. So in this scenario, Ikra loves watching reruns of her dad's favourite sci-fi series. So a lot like the original Star Trek, but not the original Star Trek. So Ikra has become alarmed at the survival rates of the security personnel, as they seem to have a high mortality rate in the show. Ikra watches all of the episodes and decides that 3 factors affect her response, which is whether all the security officers shown in a particular episode survive or not. The 3 factors she identifies are 1, number of shots fired, 2, whether the team beamed down to an alien hostile planet, and 3, whether they encounter an alien. So establish if any of Ikra's predictors are significant to the response, then evaluate the probability for a range of values within the significant predictors and display this information in a graphical format. For all levels of the significant categorical predictors, what is the probability that a security officer will survive if 20 shots are fired? Okay, so that's what we're going to be working through. So I've downloaded the data, put it into Minitab. I've got 4 columns of data. Column 1, status, is my response data. So this is whether the poor security guy died or survived the episode. Then we have the 3 predictor columns, alien encounter, which has levels of yes and no. It's obviously a categorical predictor. A continuous predictor is shots fired, the number of actual shots fired in the episode. And then beam down is whether they beam down to an alien planet or not, and that's a categorical predictor as well, with levels of yes and no. Let's form the model. I'm going to go to Stat, Regression, Binary, Logistic Regression, then Fit Binary Model. Okay, so that's the right format for the data, and our response, as I said before, was status. And I'm going to keep my reference event as survived. That's fine. Continuous predictors are shots fired, and categorical predictors are alien encounter and whether we beam down to the planet or not. Now I do want to explore higher level terms as well, so I'm going to go into Model, highlight my predictors, and then add the interaction terms for second order interactions. Click Add. There's 3 of those. Then I'm going to click on Terms through order 2 for quadratic terms, and there's only one of those because there's only one continuous predictor. Click on that, and that's shots fired times shots fired. Okay, now I can execute the procedure and produce the model. Okay, so when we look at method, we're using the logic function again. Categorical predictor coding is 1 and 0 as expected. There was 48 rows of data. Our reference event occurred 21 times and died occurred 27 times. So let's have a look at the deviance table and look at the p-values. Okay, at the moment we've only got one significant predictor, which was alien encounter. So now I'm going to reduce the model because nothing else is significant. I'm going to start off with my quadratic term because that has the highest p-value. So bring up the terms again, get rid of the quadratic term, shots fired, run the model again, have a look at the deviance table. Okay, the p-values have changed slightly. I've now got 2 significant terms, shots fired and alien encounter. I'm now going to remove the quadratic terms. Let's do this manually. So we're down to the default model with the 3 predictors. Click OK. Now we see beam down isn't significant, so I'm going to remove that from the model as well. Okay, so that should be our final model now. You can see the model summary there and the coefficients, and then the odds ratios for the continuous predictors and categorical predictors. There's 2 separate tables here because the calculation is slightly different for both. So for the continuous predictors, for every increase in the number of shots fired, the probability of survival changes by a factor of 0.932. So this means the more shots that are fired, the less likely it is the security guy will survive. Okay? Categorical predictors work in a slightly different way, in that the odds ratio is the ratio of the probability for survival with alien encounter at yes divided by the probability of survival with alien encounter at no. And because that value is less than 1, if you have no alien encounter, you are much more likely to survive. We then have the regression equations for the 2 levels of alien encounter, and we have the goodness of fit tests, which tell us whether we have a good model or not. So for these tests, the null hypothesis is that the data fits the model, and in this case, because the p-value is high, we know we have a good model. The next part of the problem is to evaluate probabilities for significant predictors graphically. So we need to graphically show and what the probabilities are. So the best way of doing that is to produce a scatter plot. But I need probability values. So I'm going to use these regression equations here and ask Minitab to give me fits for the data that we have, and then produce a scatter plot. So I need to rerun the model, and I'm going to ask for the fits to be stored. So I need to click on the storage button and then click on fits for those to be stored, and then rerun the model. I'm going to click OK and OK again. If I go to the session window, I can have a look there. So these are my probability values for different levels of shots fired and alien encounter, because that's what was in the model at the time. And let's produce the scatter plot. Graph, scatter plot, and I want with connect lines and groups. So I want my probabilities to be on the y-axis, and then the x variable is shots fired, and I'm going to have that grouped by alien encounter. Click OK, and then just enlarge that so you can see that. So you can see if there's no alien encounter, probability of survival goes up considerably. You can also see the more shots that are fired, the probability of survival goes down. The final part of the problem asks us, when 20 shots have been fired, what will be the probability of survival at the different categorical levels? Now, I could draw lines and then make a guess from there, but it's a good excuse to show you how to predict probabilities using Minitab menus. So click on Stat, Regression, Binary Logistic Regression, and then Predict. Okay, so the response is status. We're going to enter individual values. So shots fired 20, and then alien encounter we can pick from the drop down. Go for yes first, and then shot fired 20, alien encounter. Click on no, click on OK. Get to the session window to have a look at the results. So prediction for status. So when 20 shots were fired and there was an alien encounter, probability of survival was 29.6%. And then when there was no alien encounter with 20 shots fired, the probability of survival increases to 0.64. So that concludes this exercise and this lesson on binary logistic regression. I hope you liked it. If you did, give us a thumbs up, and also think about buying the book, which has many more exercises and different topics in it. Thank you. Goodbye.